Okay, so boleh start balik. Okay, cool. So just now I mentioned about the motor, the kind of motor. So we can have the shunt motor, we can have the separately excited motor, we can have the series motor, we can have compound, and also in this part also we study the motor starter, how we start the motor. There are ways to start the motor. You cannot just connect the motor to the supply. So otherwise, you know that the motor have problem with the starting current very very high. So that mean we need a starter for the DC motor, so that when at starting we can control the initial current. This look the motor picture look like lah. Yeah, you can get this picture from the Google and so on. This is this motor look like, and this structure. You can see that the shaft there, and the shaft there where it connect to the uh, blade and so on or compressor and so on lah. Can be direct coupling or can be the through gear lah. Can see like that. Okay, this is a DC motor as we know before. DC motor have two terminal, two terminal where the first one we call it the VA, which is we apply the current to the armature, and the other one is VF lah. If the motor is self-excited motor, so the separately excited motor, then we definitely we need VF field because we need to supply flux here also. So when the flux, the main flux for the machine so we got main flux for the machine, and the current flow through the armature circuit, and we know that when you got the current, you got the flux. What happened to the motor? Use the right and left hand rule of the Fleming. You got flux when the conductor carrying current exposed to the flux, then it will experience force, torque. The torque will be produced. Yeah, this is a basic thing about the machine. You must know that. We must apply current there. So the current must apply there, flow there. Then, and also the machine must have main flux from the VF. So when the current expose the flux, it produce torque. Okay, this is a basic law of the motor movement motor movement. And we know that the bigger the current, the bigger the torque produced. And the bigger the flux, the bigger the torque produced, because the torque proportional to K flux IA. Torque equal to K flux IA. You must remember the formula that we studied before. So, and here is your motor shaft. Just now I show you shaft there connected to the load lah. It can be directly connected or it can be through a gear. So here just show you how the motor. So the motor, when you apply the voltage current, it produces torque motor. The torque motor will connect the shaft to the mechanical load, for example, to the fans, to the blowers, compressors, and so on by direct coupling or by through the gear, depending on application lah. Okay, so when the motor create dia punya own torque motor, and when motor try to rotate the load will produce dia punya own torque. They call it load torque, T load. So the T load always oppose the motor torque. When the motor try to move the load torque will produce dia punya own torque, which we call it load torque. The load torque depend on the device here lah, on the mechanical load. Different mechanical load, different load torque profile like that. Similar for the motor lah. Different motor kind, it produce different motor load torque speed profile for the motor, depending on what kind of motor we use there. So the motor also has the load torque profile on itself, and the load torque also has the load torque speed profile dia punya load side. So depending. So when we choose a motor to drive a load, you need to be careful about the torque speed profile for the load and also for the torque. Otherwise, the motor cannot drive the load. If the torque is not properly used, properly selected, then the motor cannot drive the load. You need to be careful lah. But at least you must know that at starting, load torque must be bigger than. At starting, motor torque must be bigger than load torque. Otherwise, the motor cannot drive the load lah. So that is the first condition you need to make sure where Tm must be bigger than T load. Otherwise, the shaft cannot be rotated lah. So this is a kind of load. It can be like that. It can be through shift like that. Call it shift. It's like normally for lift system lah. For the lift system, they use this kind of connection where we have the shift here, and we got the gear ratio, and this is your motor. Okay, so motor connect to the gear first, and then your gear ratio drive your shift, and this your cage like cage lah, apa ni, macam lift system kan. You got cage where people come in here, and this the lift also must have counterweight. Okay, just like that lah. So when motor rotate clockwise, the lift will go up like that lah. The speed will go up, and the motor rotate anti-clockwise, the lift goes down. Ada the system where there are many system basically how motor drive the load lah. If this is like fan only, simple fan kan, so direct coupling, that is you got fan there, there's direct couple, no need shift or gear ratio, just like that, direct coupling. But if the system like a lift system or some other system, they may be required this kind of system. We need motor, we need gear, counterweight, cage, and so on. This we call it lift or hoist system lah. So now you know something about the motor. Okay, for the DC motor, some application requires the control speed. Some application require control torque, depending on application. Some application we need to control the speed. We need a variable speed drive, and some other application we need to control the torque. Okay, tengok what kind of application lah. In order to control the torque or speed, okay, or the motor, then we need to know torque speed profile. Torque speed, this is torque versus speed. T versus W mean torque versus speed, or characteristic of the motor, and its mechanical load. This is very important lah. We need to know torque speed characteristic of the motor, and also the torque speed characteristic of the load. The intersection between these two characteristics, motor characteristic and load characteristic, will determine the operating point. Okay, so that's how the system works. So whenever these two lines meet each other or intersect each other, then this is your operating point. Your speed, your torque, and so on happen at this operating point lah, like that. Show you. And later on you can see what meaning by that lah. Now first we go to the shunt motor. Go to the shunt motor. This is a basic motor. We go to this slide first. Okay, later on we go back to our previous slide 3.3. And then we combine together lah. Some material is here, and some other material in that 3.3 slide. Okay, doesn't matter lah. We just follow this thing first. This is a shunt. Okay, you see this shunt configuration. Now the armature is connected with the feed with the parallel configuration of shunt. So you got armature circuit there, RA, and you got field circuit represent IF, RCF, and RCW. Same like DC generator last time, but the supply come from V terminal now. This is different. Okay, so we apply voltage here at V terminal. Okay, the current will flow to the IA. Okay, and then at the same time the V terminal also supply IF to the field. So this IF create main flux for the field. So this flux interact with this IA, produce torque, motor torque, or you call it TE lah. TE stand for the electromagnetic torque of the motor. And when you got the torque, it produce speed. And the motor, when the motor start to rotate, it will generate load torque there, or mechanical load torque there. So that's the system. Simple lah. So hopefully you can draw the diagram for the shunt motor here lah. So by looking this diagram, very easy lah for us to create the equation here lah. So we can see that V terminal equal to IARA plus EA. Okay. And then I terminal equal to IF plus IA. This for shunt motor. Remember, the formula may be different from the other motor. So you need to see each motor. Okay. EA here induced voltage, or sometimes for the motor you call it the back EMF lah. The name for EA ni back EMF. Back EMF equal to K flux speed. The bigger the speed, the bigger the voltage induced here. Okay, and the bigger the flux, the bigger the voltage induced in this armature circuit here. And then torque developed equal to K flux IA. So this is a basic equation for the shunt motor. Okay, so what is different with the generator? So if you talk about generator, we have EA there. So EA equal to IRA plus V terminal. So don't get confused with the generator, shunt generator. The equation almost similar, but the sign here, if it's generator, it must be minus there lah. Minus there. Okay. No, minus somewhere there. So E equal to V plus IARA. when the generator IA is reverse lah. Like that, lah. When generator IA is reverse, I come out from this armature. Okay, so K flux peak or E equal to V terminal minus IARA, and then we know the speed equal to this one. Okay, for when we talk the motor, basically we want to know the speed regulation or how we control the speed. If we talk about generator, we talk about the voltage regulation. So that's different between the generator and the motor. Okay, the speed you must know to derive this one. This is a basic thing you need to know about the motor lah. Derivation of speed equation. For the shunt motor, the speed equal to V terminal minus IARA divided by K flux. The speed of the motor here. How we control the speed here in the motor? You can change the voltage terminal. Okay, we can change the RA. You can change the flux or IF lah. There are three methods to control the speed basically. We can adjust or we can configure this equation by changing the IA with respect to torque. Because IA is proportional to torque. So the bigger the torque, the bigger IA, right? So this you can rearrange the equation with respect to torque lah. So speed equal to V over K flux minus RA torque divided by K flux squared. Boleh ya? You have to do some job here lah to get the speed equation from the shunt configuration. Okay, so based on this equation, speed equal to the speed can be controlled by three ways lah. Control the flux, control the IF, control the armature voltage V terminal, and control the armature resistance RA. Since RA is fixed here, that means you need to put external resistor RA. You need to put RA extra. Then you can control that. Then you control the IA. Otherwise, you cannot control the IA. Right? RA is fixed. RA is armature resistance. So you cannot control that one. So in order to control this current here, then we need to put external resistor RA extra in series with this RA. Okay, clear? So that's how you control the bank. If you see the glance, then you can see that if we decrease flux, the speed will be increased. The lower the flux, the bigger the speed. Simple like that lah. And the voltage, the bigger the voltage, the bigger the speed. And for the RA, the bigger the RA, the lower the speed. You can see this equation. You put RA bigger, the speed lower. Okay. You put the V terminal bigger, the speed higher, right? And then you put the lowest flux, and then the speed is higher. So that's three methods to control the speed of the shunt DC motor. Actually, it's almost other motor almost similar also lah, but you need to do some adjustment there. You need to see the things first. Okay, now we try to plot the V terminal control. Okay, if we control the V terminal of the motor, DC motor, what happen now? You can see here based on this formula lah. Speed versus torque. So the bigger the torque, this is zero torque or no load torque here. Or zero current lah. Or you can see that the motor free running. The motor shaft is free running. It's not connect to any load, just free running or no load. You can see that no load condition lah. No load means torque equal to zero. So at this point, torque equal to zero. This is your speed. This is no load speed here. No load speed, no load torque. Torque equal to zero. When you increase torque or we increase IA, same lah. Just now you got two formula right here. IA and torque. Same thing lah. You increase IA or you increase torque, what happen to the speed? Can have this kind of speed. So the bigger the torque, the lower the speed. You can see that like that. So you put the higher much loading. Torque mean loading lah. Loading. That means like your car lah. Like no passenger, meaning that speed equal to zero torque. Okay. I mean, if your car have no passenger, that means it's a no load condition lah. No load condition. You put one passenger, the speed will drop a little bit. Okay. You put two passenger, drop more. You put 10 passenger, what happen to speed? Going down. So slow lah. I mean, that's meaning by torque lah. Torque something that you loading your car or you loading your motor. Okay. We can make an analogy like that lah. You drive the car or your motorcycle. The bigger the people inside your motorcycle, what happen to speed, it will drop. Simple like that. So you can see the relationship here. You can plot this one. Right. This is a wearing terminal. This is motor characteristic. Motor characteristic TM just now. And load torque now. TL. Load torque determine or depending on the what kind of load we use lah. What kind of load. Some load like that. Some load constant. So this we just take arbitrary values on here. This for example fan. Fan will look the curve of fan kipas. Dia punya curve something like that lah. Dia punya almost like that lah. Dia punya like it's not linear, it's like non-linear relationship. Okay, this is load torque. So intersection here, titik pertemuan intersection there, we give you the operating point. Okay, you can see there. This is no load speed which is given by K Vt over K flux here, and then this intersection there point. That's it. Okay, the first intersection here, your operating warp speed, operating torque at V terminal 1. If you reduce V terminal 2, then you got this characteristic, the number 2. What happens when we reduce voltage? We got lower speed lah. Lower speed and lower torque here lah, like that. You got like that. If you want to make it lower, much lower speed, the voltage must be reduced. Then you got this one, and so on lah. Understand lah? So in order to make it the speed lower, so we can change the voltage. The lower the voltage, the lower the speed lah. The higher the voltage, the higher the speed. How to determine the operating point? The intersection there lah. That is for operating point particularly. Okay. So this we draw the speed versus torque. If you draw torque versus speed, that means if you take this torque you put here, the speed you bring here, then you can see the punya relationship almost vertical lah, vertical. Ini horizontal lah, horizontal punya, horizontal. But you make this speed, torque versus speed, then you can see the curve will be vertical one. So sometimes you see they put different configuration, different ways. They plot TE versus speed, and you can see the speed will look like vertical punya line lah, vertical line. Okay, but here because they put speed versus torque, you see the horizontal line. Okay, that has happened when we reduce speed lah. So that basically simple lah. We know that in order to control speed, just control the voltage. So but the problem with this method, we require variable DC supply. We need variable DC supply to change the voltage terminal. Then basically because of that, they are expensive lah. And this method almost is quite expensive compared to other method lah. But the good thing about this method, dia punya wasp speed regulation is quite good. Quite good. I mean that no load speed and full load speed, dia punya different very small, not too big lah, not too big. They're different there. Here, different here, right? You can see the different. No load, full load, no load, full load, right? But the different very small. That's why this method commonly used to control the motor speed. They change the voltage. Okay. Variable speed ni, in order to get the variable speed for the V terminal, what you got to do? You can use for example, if you study powertronic before, you can use the chopper circuit, chopper drive, they call it chopper. Chopper mean DC to DC lah. You chop DC to small voltage to the variable DC, then you drive the DC motor, chopper circuit. Or we can use the SCR control rectifier. If supply is AC, then in order to get the variable DC, we use the SCR or control rectifier, call it. So by using control rectifier, we can have variable DC to drive DC motor. Okay, depending on what kind of supply you have lah. If your supply DC, then you have to use DC converter, or you call it chopper circuit. But if you supply AC, then definitely we need to use rectifier circuit, variable circuit, or you call it control rectifier. Boleh ya? So you need to know how to sketch roughly lah when you change the voltage. And this is speed that we intersection here lah. Intersection got 1 speed, 2 speed, 3 speed and so forth. So the lower the voltage, the lower the speed. Okay, next method we use the RA. Okay, RA is the resistance of the armature. But definitely we need to insert the external resistor series with the resistance of the armature. You need to put resistance extra in the armature circuit in series lah. Then this what happen now. Because this is a no load speed, use this formula. So in this method, flux and voltage must be kept constant lah. If you use this method, that means the flux and voltage must be kept constant. You just change RA only. Similar for the previous one, when you control the voltage, the flux and RA also must be constant. So just one parameter only control at one time. If you want to change the speed using RA, so V terminal must be constant, fixed, and flux also must be fixed. Then just change RA only. So this is the plot when we increase RA. Okay, this is load torque. Okay, remember the red color is represent load torque. The black color line here represent the motor torque. Don't get confused lah. This is motor torque profile. Torque speed for the motor yang ni. When we change RA, what happen when we increase RA? You can see you got this one line. Then you got speed here. One speed right here. And then you want to get lower speed, you have to increase RA higher. Then you got this speed. Okay. Then you want to much lower speed, then you go to the higher the RA. Then you have this intersection lah. Okay, so this is simplest punya control lah. Just put RA, simple control. But the problem with this method is, what is the main problem, you think? First, losses, I squared R. The losses in the system, that means the system is not efficient. The system, the regulation, speed regulation with this method is not efficient way lah. You got a lot of losses in the RA. The second thing, you have problem with the speed regulation, especially at lower speed. You can see at lower speed here, the speed regulation between no load and full load, very big difference. That means we cannot control we cannot regulate the speed from no load to full load. Big difference. From here to here, big difference. But for the high speed, still okay lah. For high speed, with the no load and full load almost very close each other. That means the speed regulation is still okay. But when you go to the lower speed, the big difference between here and here, which is not good. So that is a difference between the width control and R control. Okay, simple control and losses in external resistor. Okay, now we move to the third one, which is the flux control or field current control. You know that flux proportional to field, right? Flux proportional to field current, IF. So based on this formula, when we change the flux or when we change the RFC, you change the RFC in the field circuit, so that current will be changed, IF will be changed. That means proportional to flux lah. When the IF change, the flux also change. So we have this characteristic lah. Okay, this is load torque. This is motor speed. This when happen when the field is bigger lah, bigger field, bigger flux. You got this peak, lower speed. In order to increase speed, you need to lower the flux. When the lower flux lower, you got this curve, the top one, the second one. Then you want to much more high speed, then you need to make it flux much more lower. You got this one. For example, this just got plot. Okay, and this is a no load speed. It's a full load speed. And this is a reduction of flux. This is a reduction of flux. When you reduce flux, it will move this way lah. The lower the flux, the bigger the speed. Okay. Understand? That's how you control the speed. Okay, this method, okay, we can change the speed also, but the problem is this method, we cannot apply for the permanent magnet motor. PM stand for permanent magnet lah. Because permanent magnet motor, our magnet is fixed. You cannot change the flux because we use permanent magnet. That means flux cannot be used, cannot be controlled. So kalau you ada motor PM, so this method cannot be used lah. But if you have PM motor, what you got to do now? You just control water terminal only. You just control water terminal, then you can control the speed. But you cannot use the flux control. The second problem with this method is maximum torque capability reduced. especially at high speed. You can go to high speed, but what happened to the torque? What happened to the flux? Reduce kan? The higher the speed, the lower the flux. What happened when the flux drop? Motor torque will be drop because motor torque equal to K flux IA. Remember, K torque equal to K flux IA. K flux IA. Okay, so when the flux become lower, torque become lower also. So that is the problem with this motor. The higher the speed, because the lower the flux, cause the torque reduction in the machine. That's problem with that. So there are win-win in the system. There are always win-win situation. And you got high speed, but it will make your torque reduce. Okay, this is a condition. Okay, hopefully everyone of you can plot speed versus torque and can explain briefly lah how we control the motor speed. And you also can draw the equation here. And this you must know this is a no load speed. This no load speed at this particular flat lah. At this flat, this no load speed. Okay. At this flat level, you got no load speed. At this flat level, you got no load speed. So there are different no load speed depending on the flux size. Okay. Okay. So what the armature voltage control just now, I mentioned just now this method armature control voltage ni. This method is the best one to control motors because this, even though it's expensive, but it can produce rated torque. Even though the speed increasing, okay, but the motor still can produce rated torque in the system. So in terms of torque production, is very good when we use the voltage control. Okay, so the motor can still retain the maximum torque capability even though the speed change. Okay, that's a good thing about the armature voltage control. Whereas in the flux speed control, the motor cannot maintain its rated torque. The higher the speed goes, the lower the torque produced. That problem with this condition. Okay, for a motor system, for a speed system, this is a general background you want to know. Okay, for the wide range of speed control of a DC motor, then from 0 to base speed, okay, from 0 to base speed, what you got to do? In order to control the speed, you just change the voltage terminal. I mean, for example, you have motor. For example, you got motor now. Say that the motor speed rated at 1000 RPM. Just like that lah. Simple example. 1000 RPM. That means from 0 to 1000 RPM, we can change the terminal voltage. You can change from 0 to rated voltage. How much rated voltage? Depend on your motor lah. Kalau you say that your motor rated voltage 200 volts, that means you can increase from 0 to 100 volt. So 200 volt to represent 1000 RPM just now. I mean, the higher it appears like that lah. The bigger the voltage, the bigger the speed. When the voltage achieve rated voltage, the speed equal to rated speed, like that. Boleh So that's very simple lah. From 0 to base speed, we control the armature voltage. From 0 to rated voltage. Above base speed, we need to move from control voltage to control flux. Reduce flux. Flux speed reduction. And that's how the system works lah. In a DC drive system, okay, from 0 to base speed, we control voltage. Above base speed, control the flux. Reduce the flux. I mean, control mean reduce the flux lah. Ini punya curve lah. Ni now we plot torque versus speed. Tadi speed versus torque. Now we plot torque versus speed. So don't get confused lah. This is a base speed, for example. This is zero speed, zero torque ni. Ni base speed. Ni dia base speed punya axis lah. Ni. That's why just now I told you right. The when you use torque speed profile, the voltage plot will be vertically like that. Dia bukan horizontal lagi, dia vertical. Because you just reverse the thing like that lah. So ni punya low voltage. This your low voltage, you got this is speed. Intersection between torque and this represent the voltage lah. Voltage 1, voltage 2, voltage 3, voltage 4, voltage 5, voltage rated. Voltage rated represents base speed. Understand? For example, here you got the motor just now I mentioned 200 volt. Right? So here is 10 volt, 50 volt, 70 volt, 100 volt, 150, 200 volts. Okay, this represents the rated voltage. So rated voltage will produce the rated speed. So this is a no load speed. This is a no load speed. This a full load speed. No load means zero torque lah. Torque pasti zero here. So zero torque means no load speed. So this is speed at no load. Okay. And when the torque increasing, and this speed will go down. Okay, from here to here. Lower speed lah. But very good speed regulation. You can see that the speed between no load and full load very, very close each other. Ini kalau you pakai shunt motor lah, very good speed regulation lah. Okay, you want to get higher speed, increase voltage. You got this line. You want to get more higher, you got increase more speed. You got this one, and until you got reach the rated voltage. That's maximum voltage that we can apply to the motor. For example, our motor 200 volts just now. We cannot apply voltage more than 200 volts. If the motor stated in the nameplate 200 volts, okay? Maximum voltage only 200 volts. That's it. So we can increase from 0 to 100 volts. So we can get the speed first, speed number 1, number 2, number 3. And at the same time, it keep you, the motor provide rated torque up to the base speed. It's the top punya line lah, rated condition. Once it reach base speed here, then you cannot further increase the voltage. Voltage already maximum. So what you got to do now? Decrease the flux. You need to decrease the flux. So now you got this line. When you decrease the flux, you got this, the first flux, higher flux, you got speed here. You reduce more flux, you got speed here. You reduce more flux, you got this speed here. So the higher the speed, the lower the flux, the higher the speed. But what happened to the torque? The torque will be decay lah. The higher the speed, the lower the torque. Like that. So that is how we control the motor. DC motor system. This DC motor speed drive. Remember, just now we know already 3 method. But why RA is not exist here? RA we assume this lossless system. So normally in the DC drive, we don't use the RA lah to control the speed. We use voltage and flux only. Okay, for the normal system like your toys, car, and so on, simple system, then you can use RA control lah. But for the efficient system, they use the RA. They don't use the RA. They just use the voltage control up to base speed, and after that they use the flux reduction to get more speed. Okay. So this region, the region here, we call it the torque, constant torque region. From 0 base speed, normally in the control system, they call it the constant torque region. So in this constant torque region, the power is increasing. Why power is increasing? Because voltage is increasing. IA is fixed. You punya field armature current at rated condition, the voltage increasing, so the power increasing lah. Power increase from 0 to maximum power. Okay. So in this region, 0 to base speed, the power increasing from 0 to the maximum power, but the torque is maintained constant. That's why they call it the constant torque region here, from 0 to base speed. Beyond that, beyond base speed, what happened to the torque? Decay. Why decay? Because flux decay. When flux decay, the torque will decay. But in this region, IA is constant, V also constant, then the power is constant. Sometimes this region we call it constant power region, or sometimes you can see we call it also the flux weakening region. Flux weakening region or constant power region lah, same area. That is how we control the DC motor. Just put like that lah. Hopefully you can understand this one. Okay. Okay, the more slide here to show you. Okay, yes. Okay, just now how we control the 0 to base speed using armature voltage, and above base speed using field flux reduction. Okay, all right. So from 0 to base speed we control V terminal here. How to control V terminal? Control if you use the chopper, you control the duty cycle of chopper. Chopper circuit, and you got chopper. Chopper mean DC to DC converter lah. So we control the duty cycle of the chopper circuit. Then we can change the voltage. When the voltage change, the speed also change. Okay, so the bigger the voltage, the bigger the speed. Until voltage reach rated condition, then they give you the base speed or rated speed. That's it. We increase from 0 to base speed. The speed increasing from 0 to rated speed. That's one way. After reach that point, if you want to get more speed of the motor, then what you got to do? The voltage cannot increase any further, fixed there. If you try to increase further, what happen? The motor will break down lah, over voltage. Over current, over voltage mean over current lah. The current will flow exceeded the rated condition. So the motor will fail. So you cannot move beyond the we rated. So you want to get higher speed, then what you got to do? Control RCF there. Control the RCF. RCF control IF. So you need to reduce IF further. And so by increasing the RCF, the higher the RCF, the lower the IF, the higher the speed. Faham? So first, use control terminal, control V terminal from 0 to rated voltage. Then we got speed 0 to base speed. And beyond that, after that, we have to use the control RCF, control flux. Okay, that's how we did in the DC drive system lah. When you have DC drive system to control speed, normally they use this method lah, this algorithm or this way, this method technique to control the speed. But there are problems they say here. There are problems. What is the problem here? If you see the topology, what is the problem there with this shunt motor? You see that when the IT change or when the IA change, the IF also change, right? That's the problem here. You cannot maintain IF at rated condition. When you change the V terminal, right? When you change the V terminal, IA also change. Okay. When IA change, at the same time, IF also change. So that will impact the motor. That means IF change, you cannot maintain the flux at rated condition. The flux will drop or whatsoever lah. So this problem with the shunt motor. Okay, they say here, control with terminal will also affect IF, field, flux. Whereas we want to maintain flux at rated condition. Okay, because we want to maintain torque, because torque is equal to K flux IA, right? K flux IA. So when we change with terminal, we want to maintain flux at rated condition. But in this motor, you cannot do that because when IA change, due to the with terminal change, then at the same time IF also affected, so which is affected your flux also. So that's one problem lah. And the second problem with this shunt motor, because we use arc resistor, it cause losses. That means the system is not efficient way. This is not work efficiently lah. You got some losses there. I squared R. So in our business, when we buy something, when you sell something, we want to try to minimize the losses as small as possible. Okay, but here we see that I squared R happened here. So that's not good. A resistance actually represent the losses lah in the system. When you see the resistance in the circuit here, when you see the R, it represent you the losses. The losses there, your motor become hit. And the power input to the motor will be less because of the losses. So how to solve the problem of this, of the RCF now? How we can solve the problem? We see now the shunt motor, okay, fine, can use, but it has some problem due to this field current impact by the change of V terminal and also losses in RCF. All right, okay, now we come to the solution. We can use the separately excited DC motor. Okay. I think you're familiar with separately excited DC generator before. Similar structure, but we have this motor. Okay, now in the separately excited motor, as I mentioned before, we have two supply. Supply for the field to supply flux for the main. Field current responsible to supply the main flux for the system. And also we have supply for the armature voltage. That means now we have two different supply for the field and for the armature. Right. So what we got to do now? Okay, so similar lah that we did before. In order to drive the system from 0 to rated speed, we change this voltage. We change this voltage supply with terminal, but at that time we maintain flux at rated condition. That means when you change IA, the flux won't change. IA cannot control the IF because it's split. Okay, there's no wires in between them. So whenever IA change or we terminate change there, IF can be maintained constant. When IF constant, then flood is maintained at rated condition. That's good. I mean, the torque produced will be kept at rated torque from 0 to base speed. In shunt motor, the torque will deviate because the flood change. Because when IF change, the flood also change. That means theoretically or practically, the flux production will reduce. Even though we say just now, you can maintain the flux constant, right? But in the shunt motor, we have problem to do that one. In separately excited, yes, because we control with terminal and the IF control independently. Okay, that means simple lah. From 0 to base speed, we just increase V0 to V rated, and this one produce torque, and the torque is rated condition because the flood is fixed. With the flood, we control IF. We don't change IF here. Okay, and then after reaching base speed, you want to get the higher speed. Then this one already maxima, Walton maxima. You cannot do it. So what you got to do now? Reduce IF here. Just now you see RCF, right? Here you can use RCF, or you can use the what call it, the control rectifier also, and just control the alpha angle lah. Control the alpha angle rectifier. You can change the IF. That mean change mean reduce lah. Reduce IF. You can get higher speed. Okay. So this is the structure. So then now they give some question here. So what happen if the system have AC supply? We don't have battery. Now we're using battery supply or DC supply. Now we say that if we have AC supply, so what I got to do now? This is knowledge of power electronic lah. We need to use knowledge of power electronic to solve the problem. Okay, if we have AC supply, what I got to do now? We must use the AC to DC converter. You need to convert AC supply to DC supply first, because DC motor require DC supply. Remember, don't apply AC supply to the DC motor. It doesn't work. You must apply DC supply to the motor here. That means we need to change first the AC to DC using AC DC converter lah, or commonly we know as a rectifier circuit. Okay, so for example, in this circuit, it show you 3-phase source. Maybe it can be single phase or 3-phase, doesn't matter lah. 3-phase source normally for big motor. Big motor require big power, big voltage. Then definitely we need 3-phase source. But if your motor small power only, then just one phase enough lah. But in this slide, we show you the 3-phase. So we got A, B, C coming, and then here we use the control rectifier, because we want to change the voltage by using alpha control, alpha angle. Just change alpha angle control, then we can change voltage DC there. Okay, at 0 voltage, alpha angle, at 0 alpha angle, we got maximum voltage. Remember last time you studied rectifier lah. Voltage alpha equal to 0, maximum voltage produced. When we increase alpha angle, we can get the lower voltage. The lower, so the speed can be controlled here. The speed become lower lah, like that. Simple like that. Similar for the field circuit. The field circuit normally depend what kind of thing. If you want to control V terminal only, so diode rectifier is enough already. Diode mean convert AC to DC, but IF is fixed. I mean, you got just one field current. I mean, if you use that one, so we can have control from 0 to rated speed only lah. But if we want to further increase the speed, then you need to use control rectifier also here. You need another circuit control rectifier in the field side, because we need to change the voltage there. Right. So that's how this system work. Simple, right? Ada soalan? Yang ni starter we go the next last lecture now. We just up to this point. Any problem for the shunt motor? Separately excited is solution only for the speed control. We can compare now lah. both can be used. You can use shunt and you can use stabilizer. But you see that the shunt cannot maintain the flux. Yeah, you shunt, the shunt cannot maintain the flux just now. That is problem with shunt motor. The rest okay lah. So basically to solve the problem, we need to get the better speed control. Then definitely we need. It shows that the best one is motor is stabilizer motor. This is the best motor lah for our system to control the speed using the stabilizer. So anything about this slide you want to question? Ada soalan? Okay, if tak ada, then